Hi there, welcome to the final instalment in trigonometric functions and graphs, and this is trigonometric relationships. And in this presentation I'm going to use screen clippings from two sources, Hayes and Harris, and also Pearson's, and we're going to include right at the end all the questions from Pearson's on this topic and some practice questions there as well with the fully worked solution, so you can sum up the whole topic with the exercise at the end. What have we got here? Well, I think you recognise this was the start of our new journey with circular functions, where we enlarged the concept of trig functions to include angles bigger than 90, and we defined them on the unit circle here, and we said the sine of theta was equal to the y coordinate of the point moving around the circle, and the x-coordinate was the cos of theta. Okay, so that's fundamental. And what are some relationships coming out of that? Well, let's look at some of these here now. Okay, and what we're going to do is go and prove those relationships, look more carefully at them, because they're going to be useful for us to simplify expressions where we are solving equations and so on. So let's go down and have a look at establishing those. Here we are. Let's have a look over on this side at doing one which is sine squared plus cos squared. If you look at this now, remember we said the x-coordinate was cos, the y-coordinate was sine, so this distance along here, the x-coordinate, is the cos theta, we're saying, and the y is the sine of theta. Hang on, look at this. Look in there, that's a right angle triangle, so what we can say is in this triangle, the square on the hypotenuse, what is that? 1 squared, it's a unit circle, is the sum of the squares on the other two sides by Pythagoras. Remember that. So there we have an interesting result straight away from our unit circle. Sine squared plus cos squared equals 1. Okay, so that could be useful, and we'll see some uses of that coming up. Let's go over here to this diagram, and what we're trying to do is look at the relationship between the cos and sine of the positive angle and the cos and sine of the negative. So let's just check the congruence of these triangles. If they have both theta in there and both the radii there are 1, or the hypotenuse, let's draw a right angle triangle here, right angle triangle there. I think you can see we have got congruent triangles. We've got two angles in one in corresponding positions and a side. So they are congruent, which means this distance here, which is the sine of theta, and this distance here are the same, and they share that distance there. So let's look at the result of that. It means the sine of theta, which is equal to this one up here, the y-coordinate. This is the same, but it's minus the sine of neg theta. And what about the cosine? That's in here, this distance in here. So the cosine of theta is exactly equal to the cosine of negative theta. That could be interesting. So what's the sine of negative 60 degrees would be minus the sine of 60. Or pi's, let's do some pi's. The sine of neg pi on 4 will be minus the sine of pi on 4. They'll differ by a negative, but the coses will be the same. The cos of neg pi on 4 will equal the cos of pi on 4. Can you see that? Okay, some interesting results there. What about the last one here? What we're trying to do is connect the cosine and sine of the angle with its complement, 90 minus theta. For example, 30 degrees, its sine and cosine, what's the relationship with the sine and cosine of its complement? 60 degrees, or pi on 6 versus pi on 3. I think you already know this one, but let's use the unit circle to prove it. So if we make a triangle here with theta in it, there, and then if we come back, there's 90 or pi on 2 minus theta, then if we make a triangle there, can you see they still have the hypotenuse equal? This angle in here is theta. The big one in that triangle is 90 minus theta, but that means some angles of a triangle, that would be theta. Can you see, therefore, that these two triangles are congruent, but the y value for theta is the x value for 90 minus theta? Okay, and the x value, let's take it for here, for theta, is going to equal the y value for 90 minus theta. They are turned around the other way. They're still congruent. They've got the same angles and sides there. So let's write that down. What have we just shown? That the sine of theta is equal to the cos of 90 minus theta. And the cos of theta is the sine of 90 minus theta. And we've already seen that, haven't we, in trigonometry? The sine of 30 is a half equals the cosine of 60. Do you want to go back and check that out in a right angle triangle in trigonometry land? So if that is 60, its opposite over hypotenuse is the same as its complementary angle 30, will have adjacent over hypotenuse. So the sine of 60 will be the cosine of 30 and so on. And we usually now go down and do this. The sine of theta in circular function land is the cos of pi on 2 minus theta, using radians and arc length and stuff, using pies. So the sine of pi on 2 minus theta, remembering that the angle of 90 is equivalent to pi on 2 arc length over radius type measure. So there we have the first three results, and these are important results in this course, so we'll summarise those in a minute. Okay, let's do the other relationships which are particularly mentioned in this course. We don't do this in great detail, and the proof of this is not included, but I want to give you some inkling. Let's have a look here at, let's say, an angle of about, I don't know, this is about, pi on 3. Let's call that angle A. Okay, so if we doubled it, where would it go? Well, if this is about pi on 3, it'd be double that, and I'll just get rid of that. It'd be double that, and it'd be over here somewhere. I might have gone too far there. Let's come back and just double the angle. It's over here somewhere anyway, isn't it? So double the angle is about like that, 2A. So what we're investigating here is what's the connection between the sine of A and the sine of 2A, the cos of A and the cos of 2A. I guess you'd like to say something like, I hope the sine of 2A is simply 2 times the sine of A. Would you? And would you like to say the cos of 2A is simply double the cos of A? I guess you can see that's not going to work. Let's see if we can see why it won't work. Come down here, and the cos, let's say the sine of this one here is the y coordinate. Okay. When we come around to 2A, it's got an x and a y value, the cos and sine of 2A. Can you see that we can't double the sine? The sine is a y value. If you doubled this, you'd go past 1. That doesn't make sense. Doubling this would be up here somewhere. So it certainly isn't like that. The sine of 2A is not just 2 sine A. You see, for the same reason, the cos is this. If we doubled it, it'd be out here. Yet they both stay within the unit circle. right? Remembering here, neither of them can be bigger than 1. Okay, can't be bigger than 1. Okay, so here, even if we make the angle bigger, it just means it's further around here. It can't actually go outside the values for sine, which are from -1 to 1, or cosine from -1 to 1, because of the radius of the circle. So these two are wrong. Don't do that. That is wishful thinking. The relationship is actually much more complicated, and it's not in this course. So all I'm going to do now is to show you that relationship that we have to know. That's this one here. So the sine of a double angle is 2 times the sine of the angle by the cos of the angle. Quite complicated. Unfortunately, in this course, we don't do some formulae and establish those formulae which are used to prove these. So we actually have to take this out of nowhere and just use it. So the cos of twice an angle is 3 different ones. Cos squared takes sine squared of the single angle, and we could use that to prove this, couldn't we? Let's do that. Because cos squared A takes sine squared A, hang on, we know cos squared is 1 takes sine squared now, don't we? Have you got that? Since we have established up earlier sine squared A plus cos squared A equals 1. So cos squared is, take it away, 1 takes sine squared. So our expression for cos squared take sine squared is 1 take sine squared A take sine squared A, or 1 take 2 sine squared A. Do you get it? Oh, there it is there. We've just proven that one. And if you replace sine squared as 1 take cos squared, then you would get that one. Uh-oh, this is getting interesting. We're able to manipulate expressions around with these new identities. These are called trigonometric identities, because they are always true. An identity is a relationship that is always true, no matter what values the variable takes in there. Identities are always identical. Let's have a look at what the IB provide us for this examination. Okay, this is taken from the information booklet where all the formulae are. So it's section 3.2 and 3.3. This is from topic 3, which is trigonometric functions and their graphs. So we know from before, tan theta is sine over cos. Cos squared plus sine squared is 1. Sine of 2 theta is 2 sine theta cos theta, and cos of 2 theta can be any of these depending on how we want the expression to look at the end to simplify it. So for example, if I had let's say I had this one, something like, let's make one up here now, something like cos 2 theta plus sine theta equals 0.5 or a half. Now, if that was an equation, we don't want 2 different trig functions in here. We could work on this one, couldn't we? Cos 2 theta, there it is. There's sines in here, so let's keep it in sines. Cos of 2 theta is 1 take 2 sine squared theta plus sine theta. Could we simplify that further? I don't know whether we could actually. I've just made that one up. But can you see the idea? It can help us, one of these 3 can perhaps help us simplify an expression and thereby solve an equation. That's what we're going to do now. Okay, so keep this handy by your information booklet so you know where it is for the final examinations. Okay, come down and let's do some stuff with this. Okay, well here's a clipping from Hayes and Harris. A little bit of a puzzle. Sine alpha is 3/5 and we're told that cos alpha is neg 4/5. Well, you might be able to just check that out here a little bit. If you have alpha in a right angle triangle, the sine is opposite over hypotenuse, you can see that this side would be 4. So the cos could be 4/5. And the fact that it's negative means it's in some other quadrant. Okay, so you could check those out. But what we're going to try and do is find the sine of 2 alpha. So write down the formula, 2 sine alpha cos alpha. Then substitute the values in and we have an answer. cos 2 alpha. What would you do? Well, probably the top one, cos squared take sine squared, and just put in the numbers they've given us. Just watch here. Negative 4/5 squared is a positive. Okay, so here are some for you, and here are the answers over here. So pause the presentation and have a go, just practicing what these expressions can do for you in finding the cosine of a double angle. What it means is, if you have something like the cosine of 84, you can relate that to the cos squared of half the angle. 42 take sine squared 42. That's the idea, relating a double angle to the ordinary single angle. Okay, have a go. I'm going to move on now. Let's go on and have a look at what else we can do. Here's another couple of exercises. So sine of alpha is 5/13. And what's that? That's in the second quadrant. Okay, pi on 2 pi, somewhere in there. And we want to find the value of sine 2 alpha. So first of all, we could use cos squared plus sine squared is 1, and put in the sine value. Then cos is there, cos squared is that, taking the root of it, don't forget plus or minus. But because we have been given, there it is, it's in the second quadrant, cos must be negative. So there's a lot of funny business going on here. You've just got to check cosine is negative in that quadrant because it's the x value there, and so we have to choose from here the negative value. And then we can put it in the formula for sine 2 alpha is 2 sine alpha cos alpha and have an answer. Do you want to have a go? Here is from Hayes and Harris, another question, and the solutions are here. Have a go, pause the presentation and check the work as you go. I'm going to go on now. Okay, so let's look at this next use for this. Just playing around, getting you familiar with what you can do, knowing these relationships. Alpha is acute, that means it's in the first quadrant. And cos 2 alpha is 3/4. Find cos alpha and sine alpha. Write down a formula for cos 2 alpha. You have 3 to choose from. Let's choose this one because we want cos alpha. Remember the ones we've got. Cos squared alpha take sine squared alpha. We've got 2 cos squared alpha take 1, and 1 take 2 sine squared alpha. We're going to choose this one because we want cos, and that's the one with just cos's in it. So we can put our cos 2 alpha in, add 1, so cos squared alpha is 7 over 8, sorry, and here then taking the root plus or minus, but then choosing the positive one because it's in the first quadrant. Remember here, both sine and cos are positive in that quadrant. The cos is this value here, so it has to be positive in that quadrant. If you want to find sine alpha now up here, we'll choose the other one. So you choose the formula appropriate to what you're doing, and then the process is the same. Okay, so if we rearrange that, 2 sine squared equals 1/4. Don't forget this. When you have a quadratic expression, you're trying to solve it, it is plus or minus the root. But we know we want the positive because, again, it's in the first quadrant and all of them are positive there. The x and y coordinates, so the cos, the sine and the tan are all positive. Okay, have a go. Here's the answers to this next one. Try yourself on that. Okay, I'm going to go on now. Are you having fun? Let's have a look at the next little bit here. Now we're going back to Pearson's to see how useful this can be in helping us solve an equation. I've already mentioned this. Now, in the steps that I've outlined in a previous presentation, we don't want mixed trig functions in here. The cos has to be changed to cos 2x. We will want to change that. So we can see if we have this, here's our graph, and we want it to be equal to 0, we can see there's potentially 3 solutions. Possibly 3 solutions here. Okay, so now what we want to do is, and they're talking about it here, we want to change the function to just a function in cosine, rather than in cosine x, rather than cosine 2x and cosine x. So here there are 3 different double angle identities. What will you choose? What will we choose? Well, there we are. We have cos x. So we will change this so the whole thing has got coses in it. So 2 cos squared x, take 1 is what we'll put in for our cos 2x. And so we get this, and then we can factorise it from that previous presentation. You can go straight there, or let P be cos x, and might help you factorise it. And of course, if you can't factorise it, you could use the formula for the roots of a quadratic. A bit longer, but you can always use that. So you then have 2 values, cos x is a half, or cos x equals neg 1. And then you go off and solve those. They've cramped it up here. I'd like you to set it out down the page. And there are your 3 solutions, as we expected from the graph. Do you get it? It's interesting, isn't it? Let's come down and have another example here. This time, express 2 cos squared x plus sine squared x in terms of sine x only, and then solve the equation. Remember, to solve an equation, we don't want 2 different trig functions, or the same trig function with 2x and x, so we're going to remove cos x, cos squared x, and call it 1 take sine squared. Now we have a quadratic in that, so that's what we will use in here. Instead of that mixed bag, we'll put our quadratic. Now, I think we need to actually multiply, or bring the 1 across to the left and multiply everything by neg 1. They've got a couple of steps in here. Okay, got the 3 over there, and then multiplied both sides by neg 1. We don't want a negative coefficient, so we've got that there. Now, can you factorise directly? Or would you rather say here, let P be sine x, just to help me through the quadratic part, therefore 2p squared take p, take 3 equals 0, and then factorise it, and then come back to sine afterwards. Or remember, if you get stuck, you can always use the roots of a quadratic if you're not too sure of the factorisation. But you must come down to these values. And then, of course, you can talk about this one. There's no solution. Sine must be less than 1. And here, this one gives us 3 pi on 2. So there's only one solution. Okay. Do you get the hang of it? Quite handy, these formulae. Okay, let's have a look at the last one here from Pearson's, and then we'll go and let you loose on a few problems, see what you think. So solve this equation. Well, first of all, you can see it's a mixed bag. We've got sine 2x and 3 cos x. So let's try and do something with this. So it's 2 sine x cos x over there equals 3 cos x. Now, it looks like we're still stuck here because we've still got a mixed bag. But let's put it all across on the left here. Okay, equal 0, because you know we usually invoke the Null Factor Law. Get a product of 2 things equals a 0. Product of factors is 0. One of those factors must be null. One of those 2 must be 0. We can factorise. So we have escaped trying to solve a mixed equation with sines and coses both in it. Taken out cos as a common factor, and then 4 sine x take 3. So we'll either have this is 0 by Null Factor Law, or this is 0, giving rise to those 2 values. Now this is a common one. You know cos x is going to be 0 when x is pi on 2. On this, look at the domain. We're only allowed to go to 0 from 0 to 2 pi, 0 to pi. And then this one, you would have to use that on the calculator. And when is sine x 3/4? Just check. There are 2 values here. So you could do that in graph mode, or you could look up inverse sine of 3/4 in radians, and it's approximately, because it's a rounded off decimal here, so that's that angle. But don't forget, you could have pi minus that angle, an equivalent angle in that second quadrant here, because sine is positive in both those. And we're only allowed to go around and go up here again, the domain only around to pi. If you check that on your calculator, what could you put in? Well, you could go and have a look at sin x equals 3/4. So draw the line y equals 3/4, and then sin x, and get these intersection points using intersect on the calculator. Okay. All right. You've got a few tools here that you can swing into action at any time. Just got to watch whether it's in paper 1 or paper 2. Paper 1, you won't have a calculator. Okay, come on down and let's do some exercises. These are from Pearson's now, and represent the whole topic 3. So it's not just what we've done here, but it's old equations as well, all mixed up. I pause the presentation, I'll go through it bit by bit, and the solutions are down below. Have a go. Let's have a look at the next few. 18, we'll just go through here to 25, and then I'll pick up 26 in a minute. So pause it there, choose some to do. You may not have time to do all of them. And we'll go through here. I think we can get them all on. No, only 26 through to 35. I think there's a bit more coming at the end. So have a go, pause that, see what you think. And we come down to, let's go there, 36 now. All right. So pausing that, having a go at pulling apart a mixed bag, some that we need to simplify with a formula, and various formulas, see what you can use. And then what we'll do now is go down the solutions and go through the 36. Okay, there's question 1. Part of question 2, let's just pick this up now. Question 2, with a bit of graphical checking there. They're using a Texas Instrument calculator here. Calculators don't vary much on that, but you can check that on your Casio or whatever calculator you've got there. Let's go question 3. And question 4. Question 5. Question 6 there. Question 7. Question 8. A lot of work here for you. Question 9. I'll just go back up a bit there. Oops, we've gone to 8. We'll just come down. Question 9. You can see that top line a bit there. Go to question 10. Question 11. I know we've got 11 through 14 all on that screen there. Okay, 15 through 17. Notice that Pearson's are using a different setting out from what I presented to you in the trig equations presentation. So you have to follow that through. They've set the k values up here, showing you which way you're going as you spin around 2 pi in either direction, and ruling them through. That's not a bad presentation. Okay, let's go down now 18 to 20. There's 20's full solution there at the bottom. 21. Okay, 22, 23. There's 24. 25. And we're coming into 26. There's two different ways of doing it, depending upon whether it's in paper 1. That's no calculator, that one. Okay, so let's look at that. And then 26b is the solution if you did have a calculator on board. That's the complete solution there. Okay, let's go to 27. Check that out a bit. Okay. Let's have a look at that. Okay, 28. $29. 30. 31. 32. 'Come back there. 33. 34. 35 and 36. Now, what we've got coming up now is Pearson's set of practice questions on the whole topic 3. So come on down and have a look at those. I'll just come up to there. There's the first 4. Now pause the presentation. The solution is going to come up down below. Let's have a look at the next few. 5 through 9. I think we can get all these on. No, just 10, 11 and 12. And there's 13. So pause those. Now we're going to have a look at the solutions. There's paper 1 type for question 1. Paper 2, or part of it, we'll just scroll down a minute. There's the rest of question 1, paper 2 approach with a calculator. And question 2 and 3 there. Question 4. Part of 5. Okay, so let's look at all of 5. Look now at 6. Part of 7. We'll bring 7 up in a minute. 7. Go to 8 and 9 now. Rest of 9 there coming up. Can we get it all on? We'll just leave that there. Part C. Rest of 9, and there's 10, 11. 12 and 13 there. Well, a lot of work there, a big unit, a very important unit. Please keep in mind that you need to memorise, I hope you've done it by this stage, memorise the cos and sine, and we can work out the tan for, pi on 4, pi on 6, pi on 3. They are important as working angles in solving equations. Well, you're doing very well. Well done on coming this far. You've built up a lot of skills, so keep practicing, and I look forward to seeing you in another presentation. Cheers for now.